In this video, we'll be looking at Chapter 14, Section E, on transforming the function y equals f of x. Now, we've seen transformations already when we were looking at modeling data using a sine curve. Remember this equation, which was the sine curve, or the model of a sine curve, and we had four different factors that affected the original y equals sine of x graph. Remember, A stretched the graph vertically, D moved the graph up and down vertically, B stretched the graph horizontally, and C moved the graph left or right. So in this section, we're going to look at some of these transformations again, and we're going to look at a few new ones as well. There are three main types of transformations. The first is a translation, where we simply move the graph up and down or left and right. The second type is a reflection, where we essentially take a mirror image of the graph across an axis or a line. And then we have dilations, and dilations stretch a graph vertically or horizontally. Let's take a look at translations in a little bit more detail. Now remember, a translation simply moves the graph either horizontally or vertically. And for a translation, we need a vector, a translation vector, that tells us how much to move horizontally and vertically. Now remember, from vectors, we have the horizontal component on top and the vertical component on the bottom. So if I know h, I know how much I'm going to move the graph horizontally, and if I know k, I know how much I'm going to move the graph vertically. Now if h is positive, the graph will move to the right. If h is negative, the graph will move to the left. If k is positive, the graph will move up, and if it's negative, the graph will move down. So if we have our original function, we're always going to start with y equals f of x, and f of x can be anything. Our image equation, or the transformed equation, is going to incorporate the vector components h and k. And we simply have our new image equation. This is the transformed equation of y minus k equals f times x minus h. And this is the transformation equation that we need to remember for translations. So let's take a look at some examples of translations. Here I have a graph of y equals x squared. Right, and I'll rewrite that without the graphing calculator notation. We simply have y equals x squared. And you'll notice that this is a quadratic function, and it's a parabola that opens up and has its vertex at the origin. Now let's take a look at a few translations of this graph. So on this graph, we still have y equals x squared. Okay, and then we have, in the blue, we have y equals x plus 2 squared. And notice here that the x plus 2 is inside the parentheses, or the plus 2 is inside the parentheses. And notice what happened to the graph. The origin moved left. It moved left. That's because, really, this equation, and let me use blue here, this equation is y equals x minus negative 2 squared. Okay? This is a horizontal translation. Now remember our image equation from the previous slide. so the altered or the transformed equation under a translation is y minus k equals x minus h, or sorry, f of x minus h. Well, in this case, the f of x is the square here. This is what we're doing to the original x. And I'm subtracting the horizontal component of the vector. So I'm subtracting negative 2. If I have x plus 2, I need that subtraction in here, so I need to alter the equation to do x minus negative 2. And that's why my graph moves to the left 2. Notice it didn't move up. That's because I have no k. If we take a look at the green graph, we see that we have y equals x squared plus 2. And look at what happened here. This graph moved up. The 2 is outside the parentheses. It's not really attached to the x like it was in the other graph, and this is a vertical translation. Okay? And notice if I wanted to rearrange the equation to make it look like my image, I could subtract 2 from both sides, so that in this case I have y minus 2 equals x squared. Well, that looks like my image equation, right? And in this case I only have a k. K is a positive 2 because the subtraction sign is built into the image equation, and that means that my graph moves up 2. Let's take a look at a few more examples. Here, again, we have the y equals x squared. This is my original function. And my first translation is y equals x plus 2 squared plus 2. Right, I'm going to rewrite that again here so that we get rid of the calculator jargon. Okay, and if I rearrange this, if I bring this 2 over to the other side, I'll have y minus 2 equals x plus 2 squared. So in this case, let me do one more thing. Let's expand it more just a little bit. So the left side stays the same, and on the right side we have x minus negative 2 squared. So in this case, my translation vector is negative 2 over positive 2. My horizontal vector, or my horizontal change, comes from this number, and my vertical change comes from just this number, not the negative sign. And so you can see on the graph that the origin of the original curve went left 2 and up 2. And so on the green graph, you can see that the vector is going to be positive 2 over negative 2. Okay, and if we rewrite that equation, I can show you why. We have y equals x minus 2 squared minus 2. Well, I'm going to bring this 2 over so that I have y. I'm going to skip a step here. I have y minus negative 2, which is the same as y plus 2, equals x minus 2 squared. So again, the negatives are built into this transformation equation, this image equation, and so I have a positive 2 in the x direction and a negative 2 in the y direction. And that's translation. So whenever you're given a vector like this, just take a point on the graph and move it over whatever that vector is, and do that for as many points on the graph as you need, and then you can redraw it. The next type of transformation is called a reflection. And remember that a reflection is simply a mirror image of a function or a graph, and it's flipped across some line. And there are three main lines that we tend to use. We have the x-axis, we have the y-axis, and we have the line y equals x. I'm going to show you examples of all these, but first let's take a look at the image equation or the transformation equation for each of these. Remember, we'll start with y equals f of x for all of these, and then we'll take a look at what y equals f of x becomes for each scenario. So, for a reflection in the x-axis, this equation or this function will become y equals negative f of x. Notice that the negative is on the outside of the function. So I'm essentially taking the entire function, whatever it is, and I'm putting it in parentheses, and then on the outside I'm putting a negative sign. For the y-axis, a reflection in the y-axis, we have y equals f of negative x. And what this means is that everywhere I see an x in the original function, I'm going to replace it with a negative x. And then for the last case, taking a mirror image across the line y equals x, the transformation equation or the image equation becomes x equals f of y. And essentially what I'm doing here is switching x and y. And so let's take a look at some examples of this. So we're going to start with y equals x squared again, this red parabolic curve right here with the vertex at the origin. And now we're going to take a look at reflections in the x-axis and the y-axis. And so remember, I had y equals x squared, and it was the same as this curve right here, except it was red. Well, that didn't go away. I still have y equals x squared graphed, but notice on top of it I have the green graph. It's an identical graph, and so I'm going to start with this one. So the green graph here is y equals negative x squared. And if you remember from the previous slide, this is really the image of a function that's mirrored across the y-axis. Because I have, this is the image equation for mirroring across the y-axis, and notice on the inside I have the negative sign. I've switched x with negative x, and that's exactly what I've done here. But when I do that with our example equation, y equals x squared becomes y equals negative x squared, the negative being inside the parentheses. Well, this simplifies right back to y equals x squared, because everything inside the parentheses are getting squared. This negative sign is getting squared along with the x. So I have the same exact graph that I started with. And what I did was I simply rotated this graph about the y-axis, and I came up with the exact same graph that I had. Okay, notice in the blue equation we have y equals negative x squared. This time the negative being outside the parentheses. And if you remember from the previous slide, this image equation corresponds to a mirroring across the x-axis. And that was with this equation right here. And so this negative sign is no longer, it's not getting squared like it was in the green one because it's outside the parentheses. So this equation simplifies to y equals negative x squared. And what happened was I took that original graph and I flipped it across the x-axis. And so now it's identical, except it's pointing down. Okay, we're going to take a look at the last type of mirroring here, and I had to do a little bit of trickery on the graphing program or calculator that I use, because it's not so easy to type in the equation of the image for this particular example. However, we're going to again start with y equals x squared. Notice that's my nice red curve, just like we've been using. And what I'm attempting to do here is really write one equation with two separate equations, because there's no way to actually do this in the calculator. So I'm going to pretend that both of these lines are blue. My image equation is really y equals the square root of x. And that should be a plus or minus square root of x. Now how did I get that? Notice that really what I'm doing here is I'm taking the mirror of this function, the mirror image of this function, and I'm flipping it across the line y equals x. I'm not flipping it across the x-axis or the y-axis. I'm flipping it across this line y equals x. And remember from our image equations that what we're doing is essentially switching x and y. Sorry, that should be a y. We're switching x and y. So if my original equation is y equals x squared, then the switched equation should be x equals y squared. Now we generally take this transformed image equation and we solve it for y. So I need to get y by itself. Well, how do I do that? I take the square root of both sides. But when I take the square root of both sides, I need to consider the positive and negative square roots. And so this is my true image equation here, which is really two separate equations. It's the positive square root of x and the minus square root of x. And that's why I had to put 2 into the equation. But if we treat these as a single function, we see that essentially what I've done is I've rotated the original graph 90 degrees to the right, or I've flipped it across the line y equals x. Alright, we're going to take a look at our last type of transformation, which is dilation. And remember, dilations are really a stretching or shrinking along the horizontal or vertical directions. So there are really 3 types of dilations. We have the vertical dilation, we have the horizontal dilation, and we have just a dilation that is essentially both vertical and horizontal at the same time. So in each case, we need a factor k. And this is kind of like the vector, the translation vectors for translations. Sorry, that should be k. We need a factor k. We need to know how much to stretch or shrink each of these graphs. So typically we'll be given that factor, and then we'll be asked to find it. So again, we're going to take our original y equals f of x equation, and we're going to find the image equation, or the transformation equation, for these dilations. So for a vertical dilation, our y equals f of x becomes y equals k times f of x. And notice that the k is on the outside of the f of x. So I'm taking that entire function and I'm multiplying it by k. For a horizontal factor, I'll have y equals f of x over k. Okay, notice this time that the k is on the inside, and essentially what I'm doing is I'm replacing each x in the original function with x divided by k. And again, I'll show you examples of this. And then the last dilation, which is really a combination of the two, is y equals k times f of x over k. And so I'm really combining both horizontal and vertical at the same time. Okay, for these examples we're going to switch to y equals sine of x instead of y equals x squared, partly because we've seen dilations with sine of x before, but also because it's just easier to see the dilations on this nice sine curve than it is on the graph of y equals x squared. Okay, so here are 2 examples of dilations, and this graph looks a little busy, but follow the colors. Notice the red graph is our normal y equals sine of x curve. Okay? And our blue curve if you look up to the top left, you see it has an equation of y equals sine of 2x, and the 2 being inside the parentheses. And let me use blue here. So we have y equals sine of 2x. And remember from our dilation equations that this actually, because the k, my k here, is on the inside of the parentheses, this is a horizontal dilation. And remember that the horizontal dilation equation was y equals f of x over k. Well, I don't have x over k, I have x times something. We're not going to call it k yet. So I can make this look like this by rearranging the equation a little bit. I'll have y equals f of x over 1/2. Remember that dividing by 1/2 is the same thing as multiplying by 2. Well, what I've done here is I've found k equals 1/2. And so really what's happening to my graph, my nice sine curve, is that all of the x coordinates of these points are being multiplied by 1/2. Right? So here this x coordinate is here, and on the blue curve it's half that distance. Here my x coordinate on the red curve it's equal to pi, so it's roughly 3, and you'll come back here on the blue curve, we see that it's roughly 1.5. Okay, so I'm taking all of the points on my red curve, the x coordinates, and I'm multiplying them by 1/2. Notice that the y coordinates stay the same. The y coordinates all stay the same, because this graph is just a horizontal dilation. All right, if we take a look at the green graph, we have y equals 2 sine of x. And this time, the 2 is on the outside. And so if you remember from our dilation equations, we have y equals k times f of x. And so in this case, I don't really need to do much else to find k. I know that k equals 2. So what's happening here is all of my y coordinates are being multiplied by 2. So again, let's go back to this point. My y coordinate here is being multiplied by 2, and that's why the green graph is stretching vertically. Here, notice my y coordinate is 0, and 0 times 2 is still 0, so on the green curve that y coordinate is still the same. And notice that the x coordinates don't change. That's because this is just a vertical dilation. Let's take a look at one more dilation. Again, we have our red original sine curve, and now we have the transformed blue curve, which is y equals 2 sine of 2x. So as you can guess, we have both a vertical and horizontal dilation factor here. And remember that my dilation equation is y equals k f of x over k. So again, I need to rearrange the inside of these parentheses to look like x over something, not x times something. So to do that, I'm going to have y equals 2 sine of x divided by 1/2, which is the same thing as multiplying by 2. So in this case, you will see that my vertical factor is 2, and my horizontal factor is 1/2. And so on this graph, if we pick a point on the original curve, notice that the x-coordinate is multiplied by 1/2. So this point shifts over to here, and the y-coordinate is multiplied by 2. So that point shifts up. And all of those points are multiplied. The x-coordinate is multiplied by 1/2, and the y-coordinate is multiplied by 2. And so these points are shifted like so. Okay, I know this video has gotten a little long, but let's take a look at just a few quick examples and then we'll be done. So for these examples, we're asked to find the image equation under certain transformations. So for the first example, we're asked to find the image equation of y equals x cubed under a reflection in the line y equals x. And so the very first thing that we need to do is find the image equation, the general form of the image equation, and there's a great table in your textbook that summarizes all of the equations that I've shown in this video. And so the general transformation equation for this is x equals f of y. So remember, when I'm reflecting across the line y equals x, I'm switching the x and y values. So to do that, I simply get x equals y cubed. Well, this gets a little tricky. How do I solve for y? Well, I need to go back to algebra here and remember that that I can take the cube root. So I'm going to take the cube root of both sides. Right, and the cube root of y cubed is simply y. So my image equation is y equals the cube root of x. And I could graph that if I wanted to. I could put it in the graphing calculator. Alright, for the second equation, I'm given y equals 4 minus x is under a horizontal dilation with a factor of 2. So again, I need to go find the original image equation for a horizontal dilation, which is y equals f of x over k, k being the factor. And so now I'm going to plug in the factor everywhere I see a k. So I'll have y equals 4 times x divided by 2 minus 1. Since this is the only place that x shows up, this is the only place that I need to add in that horizontal factor. And I can simplify a little bit from here. Right, 4 times x over 2 is simply 2x. And I have, don't forget the minus 1 at the end. And so this is my image equation for the second example.